Hello everyone, this is Russell Kim, and I'm currently a senior studying chemical engineering at Lehigh University. For the last 1.5 years, I've been working with Professor Elsa Rekmanis and her graduate student, Mongting Sun, to study the charge transfer properties of an organic semiconductor. And right now, I'd like to present my poster, which is characterization of active layer and electrical properties of P3H2-based organic field effect transistors. So, to break it down, there's P3HT, which is poly-3-hexylthiophene, and OFET, which is an organic field effect transistor. P3HT is basically a representative polymeric semiconductor. It has conductive properties because it is pi-pi conjugated structure. What does that mean? It's like benzene organic chemistry. It's like a benzene because it has a ring structure with double bonds, or more specifically, delocalized electrons. This allows P3HT to exhibit stacking properties on its thiophene rings that improves the regularity of the polymer and leads to promising electronic properties. In simple analogy, it's like a conductive graphite, except the hexyl side groups on P3HT make it semiconductive. On the other hand, OFED is an organic semiconductor made of 4 layers: the substrate on the bottom, covered by the gating dielectric layers, and finally, the source and drain ports. OFEDs are rising in popularity because of the demands in biocompatible sensors, easy fabrication, and large-scale processing. Our OFEDs are made at Lehigh in an ISO 5 cleanroom. As a note, the molecular structure of P3HT and a schematic of OFED can be found in Figure 1. Now, the characterization involved in UV-Vis, which is ultraviolet visible light spectroscopy. Because every molecule absorbs visible light at a unique wavelength, hence the colors we see. On a smaller wavelength, where our eyes can no longer perceive, subsections or subregions of every molecule exhibits a certain response when struck by ultraviolet light. Therefore, UV-Vis spectroscopy is a ubiquitous choice in polymer characterization. And for our project, it tells us how well our coating technique allows P3HT to adapt to its conjugated nature. For the P3HT side of the experiment, we begin by weighing solid P3HT using a weighing paper. Typically, we extract 2 to 3 milligrams of P3HT and dissolve it with chloroform at a 5 milligrams per milliliter ratio. In our case, 0.4 to 0.6 milliliters of chloroform. Because of the physical properties of the P3HT solution, such as volatility, we must use a well-sealed amber vial, where it can block light. Then, we add in a magnetic stir bar so that the solution can now be mixed at 55 degrees Celsius at 650 rounds per minute. To prepare a well-mixed solution, 30 minutes of stirring is recommended. For the OFIS side of the experiment, we begin by cleaning the wafers using acetal, methanol, and isopropanol. This is to remove contaminants, such as dust and oils, as well as to enhance the adhesion of the coating. Then, we send the wafers in for 15 minutes of plasma surface treatment. After the conclusion of solution preparation and wafer cleaning, we perform spin coating by dropping 45 microliter of solution onto the wafer. This coating on top of the wafer is better referred to as active layer. For UV-Vis analysis, we drop the solution onto a sanitized square glass slide. The coating process is done by spinning the wafer or square glass slide for 1 minute at 1,500 rounds per minute. An important practice to remember here is that the amber vial with P3HT solution should minimize contact with air because it is volatile. In other words, it evaporates easily. Therefore, the wafer or glass slide should be quickly spun as soon as the solution is dropped. As a note, the prepared P3HT solution and OPUS sample can be seen in Figure 3. Once the samples are prepared, the wafers are sent into a glove box for characterization using a probe station. The probe station is set up such that one probe sits on top of the source electrode, one probe sits on top of the drain electrode, and the last probe touches the gate electrode. Refer to Figure 1 as needed. This produces the left and middle graphs shown in Figure 4. Then, the key values from the graphs can then be used to calculate electromobility through the equation found in the middle of results and discussion. Once the class slides are prepared, it is sent to a UV-Vis spectrophotometer to produce the right graph shown in Figure 4. In Figure 4, the left graph is referred to as the output curve. An output curve basically describes the relationship between drain source current, IDS, and drain source voltage drop, VDS, across the two ends of the probes. The key values we want to see here are the saturation currents at maximum voltage drop of -80 volts under various applied gate voltages that also range from -80 volts to 0 volt. Now the negative signs are applied here because it involves electrons, which have a negative charge. The middle graph is referred to as a transfer curve. A transfer curve basically describes the relationship between drain current, ID, and gate voltage, VG. The key idea we want to see here is how well does the electron move at various voltages. Therefore, with those two sets of data, we calculate the average electron mobility of spin coating to be 0.03 centimeters squared per volt per second. This number means for average voltage applied in a second, the electrons move in 0.03 centimeters squared of area. On the right of figure 4, we see a UV-Vis plot where absorptions at 605 nanometers and 550 nanometers are observed. A broad and strong peak at 650 nanometers represents the 0-0 transition of P3HT. This is associated with this intrachain interaction. The stronger the peak, the greater intrachain interaction, the longer conjugation length, and the better planarization of the polymer backbone. A narrower and weaker peak at 550 nanometers represents the 0-1 transition of P3HT. This is associated with its interchain interaction. To picture what intrachain and interchain interactions mean, refer to figure 2. Currently, we are exploring alternative coating methods such as plate coating and convective deposition, where they should improve the charge mobility by facilitating the orientation of aggregates. We are also working with P3HT blends, predominantly PEO, polyethylene oxide, to increase the crystallinity and tune the film morphology to improve electrical properties. Additional characterizations such as Raman spectroscopy, atomic force microscopy, increasing incidence wide-angle X-ray scattering are also being used, especially because they provide a clear insight into the film morphology, molecular stacking, and crystalline regions. These findings provide fundamental insights that contribute to the future development and commercialization of not just P3HT and OFET, but more importantly, the whole semiconducting field. This will conclude my presentation. I thank you all for tuning in, as well as the opportunity from David and Lorraine Freed Undergrad Research Symposium.